Good morning, everyone. This is Bill Goebel. I am from FMEDA, and this morning we are going to do a web seminar on FMEDA, failure mode effect and diagnostic analysis. Hopefully you've heard of this technique before, but even if you haven't, we're going to definitely teach you a little bit about it today because it has a whole lot to do with certification and following functional safety standards. Brief background: a lot of my career has been spent doing electronic design, software design, and functional safety work for about the last 15 years. I've been very heavily involved in the development of the FMEDA technique, and hopefully we can give you some insight as to what this is all about, why it was created, and how well it works. Overall today, I'd like to just remind you I am from FMEDA. FMEDA is a company that does functional safety, cybersecurity, and integrity certification. We have offices around the world, and we spend all of our time working on functional safety. We have a lot of engineering tools for end user, project level work, and for product development work. I'm proud to say that FMEDA has written and published many, if not virtually all of the books that have been written on functional safety and control system reliability and availability. FMEDA certification is a subsidiary, independent subsidiary of FMEDA, based in Geneva, Switzerland. FMEDA Certification SA offers the Integrity Certification Program, which includes functional safety, availability, security, and usability. In effect, we believe we've created a whole new concept in certification. Today our topic is FMEDA, but I'd like to start the web seminar by saying that, reminding everyone that in the IEC 61508 functional safety specification, or standard I should say, there's two fundamental concepts. How do you achieve a safe design? First concept is follow a detailed engineering process, which is called the safety life cycle. Second concept is probabilistic performance-based system design. And what we mean by that, and it's focused primarily on random failures, hardware availability. And what we mean by that is we need to evaluate the probability of failure of a particular safety instrumented function. Of course, in order to do that, we need to know what are the failure rates as a function of failure mode. It's also very important that we understand how good are any automatic diagnostics built into the system. And the reason that's important is automatic diagnostics can convert safe failures, dangerous failures into safe failures, and so forth. We'll be talking about that a little more as we go through. FMEDA is an essential part of the probabilistic performance-based system design concept. FMEDA is an essential part of product certification per IEC 61508, which we will talk about. And manufacturers who get certification will typically do an FMEDA analysis. I'd like to say there's two reasons. Number one, it helps demonstrate, it shows compliance to many of the requirements of the standard, but perhaps more importantly, it gives relatively accurate failure rate and failure mode data needed by system designers at the project level to actually design safety instrumented functions. One of the main reasons for FMEDAs, as we talked about, was to show compliance with IEC 61508. And in fact, the FMEDA analysis technique was developed by FMEDA engineers to show compliance to many of the hardware random failure type requirements of 61508. An FMEDA is an analysis technique that provides a measure of diagnostic effectiveness and an accurate measure of failure rates as a function of failure mode. Why do we care about this stuff? Well, automatic diagnostics can have a significant impact on the safety of a product, of a system. Because if automatic diagnostics detect a failure that's potentially dangerous, they can enunciate the failure and repairs can be made. In some applications, it's appropriate to initiate an automatic shutdown. You don't want a process even running if the safety protection system is not capable of responding to a dangerous condition. So diagnostics have a major impact on functional safety. This is clearly recognized in our functional safety standards. And the problem was, and quite seriously, the problem was, like in the mid-1980s, everybody defined what diagnostics was. They could give you a nice mathematical, theoretical definition of diagnostic coverage factor. But nobody had an analysis method to measure diagnostic coverage. And of course, to really do a good job of probabilistic modeling, we'd like to know what the diagnostic coverage factor is for both safe failures and for dangerous failures, at least as defined by IEC 61508. Many of the PLC manufacturers who were designing products in the mid to late 80s realized that the automatic diagnostic capabilities of the microprocessors could be used to greatly impact both safety and system availability. Diagnostics can be used to increase safety and reduce false trips. And that led to new architectures being designed. Architectures with names like 1 out of 1D and 2 out of 2D or 1 out of 2D. These architectures were designed to take full advantage of the automatic diagnostics, to reconfigure the system to achieve higher levels of availability and safety. If you do a lot of probabilistic modeling, you've probably seen numbers like these before, but in fact it can be shown that for a good level of automatic diagnostic coverage factor, like 95% plus, these new advanced architectures can achieve higher levels of availability and safety than any other architecture. These particular numbers were based on simplified equations with assumed failure rates and diagnostic coverage factors for comparison purposes only. If you'd like to see the details, let us know. They are published in the ISA book, Control Systems, Reliability and Safety. What is an FMEDA? Well, it's defined as a structured, quantitative analysis of a system, subsystem, product, or component. It is done to predict failure rates, failure modes, and the effects on system operation while taking into account automatic diagnostic functions. An FMEDA is an expansion of the decades-old and well-proven FMEA technique. Many of you who have been around the field of reliability engineering know that FMEDAs were developed in the mid-60s. The history of reliability engineering that I read says they were developed during the Minuteman rocket program in the United States, and it turned out to be an effective method to find design defects. Over the last 40 to 50 years, this method has been expanded and is pervasive in many industries. It's a bottom-up technique where an entire system is analyzed one component at a time. Therefore, of course, it's very systematic and, quite frankly, In my personal opinion, it's very boring, but people do it because it works. It really finds problems. The FMEDA is an extension of FMEA, developed in the early 1990s by Exeter engineers. To expand an FMEA, a quantitative failure rate column is added. Diagnostic probability columns are added for both safe failures or dangerous failures as a function of failure mode for every single part. And the result is an analysis technique that provides both functional failure rates and failure modes and the main categories required by IEC 61508, safe failures, dangerous failures, and so forth. An FMEDA has proven, the FMEDA technique has proven to be the best technique for generating failure rates of instruments that we use in our safety instrument and function designs. Now, the concept of an FMEDA is pretty simple when you think about it. If you have a product like a pressure transmitter or a valve actuator assembly, you could get the failure rates and failure modes from good field failure data records. The problem with this is to identify all the failure modes, it takes a lot of statistics. And in fact, this level of statistics is not being gathered anywhere. And if we just don't have enough information, enough statistical records to generate failure modes and failure rates from this kind of product information, the way to solve a problem is a classical engineering approach: break the problem into smaller pieces. So I'm not going to look at a whole valve, remote actuated valve assembly. I'm going to look at an actuator and a valve, and in each valve, in the actuator, for example, I'll look at every structural member, every spring, every diaphragm, every piston, and at that level, I have good failure rate and failure mode data on the components. So we just sit down using an FMEA style technique and look at each piece individually, determine how the component failure will affect the instrument, and then sum up the results. From an engineering perspective, it's a classical engineering technique. Break the problem into smaller pieces. Using a component database, the failure rates and failure modes for a product can be determined more accurately than any field failure data technique that I have seen to date. A failure mode effect and diagnostic analysis is follows a tabular format where you go through a design, and for any given piece on the design, we list the component. For each component, there's a list of all known failure modes, the failure rate, and the distribution of what percentage of the total failure rate for the component is responsible for each failure mode. And for any given part and any given failure mode, we can list, is there a diagnostic, and what's the probability that the diagnostic will detect a failure. The result of that is a detected or an undetected failure, and the mode is dependent totally on what happens to the instrument, or what happens to the subsystem, if you want to call it that. So the end result is, for each particular failure mode of the instrument, we have total failure rates, and of those failure rates, we know how many of them are detected and how many of them are not detected. The functional failure mode is the most basic type of FMEDA because, like an FMEA, the functional failure modes of the product or an instrument is identified depending on the functional failure modes of the components. If you've got a pneumatic actuator, for example, and the diaphragm bursts and the pressure is vented, And the spring will move that actuator to its fail-safe state. And so one particular failure mode of a diaphragm might be large leak or heavy leakage, and the failure mode is valve or actuator moves to safe position or to resting position. That would be a functional failure mode of the actuator. Whether that's fail-safe or fail-dangerous depends on the application, of course, and we'll save that discussion for a little later. Given a particular application, or given a definition of an application, all these functional failure modes can absolutely be classified as dangerous or safe, depending on the definition. This particular definition for dangerous comes from IEC 61508. The definition for safe is not the 61508 definition. It's the new version of 61508. This is the definition from the new version, which is actually much superior in my opinion and easier to understand. I would like to comment that in reality, when you convert functional failure modes of a component into IEC 61508 categories, sometimes you can't determine whether a functional failure mode is safe or dangerous unless you know the application. So that classification has to be done by the system designer. For example, in the case of this Rosemount 3051S SIS, this is a sheet of data from the EXIDA Safety Equipment Reliability Handbook, and you'll see a failure rate called fail low and another one called fail high. Those are the failure rates for those particular failure modes. Depending on low, may or may not be safe. If it's a low trip, where a low signal causes a trip, fail low is fail safe. However, if it's a high trip, fail low must be classified as dangerous. This has all been written up in detail in some of our books, but I did want to tell you that sometimes FMEDA results must be a combination of 61508 numbers and functional failure modes. Many of you by now have caught on to the fact that the accuracy of an FMEDA depends on the accuracy of the component database. If the component database is full of garbage numbers, the FMEDA analysis will generate garbage numbers. Therefore, of course, the component database must include good, reasonable failure rates, or perhaps even conservative failure rates, and failure mode distributions of each component. Because if there's some particular failure mode of a component that's not listed in the component database, it's not going to be part of the FMEDA. That's why this database is so important. Given that it's so important, well, where do we get this data? There are many component-level databases available in the world today. Some of you would recognize the Siemens 29500 database. It's primarily electronic components. The old Mill Handbook 217F was the primary standard back in the 80s when I learned some of this stuff. Bellcore, a telecommunications company that has ceased to exist, had a database. IEC 62380 is a relatively recent standard from IEC that also provides a database of primarily electronic components. One of the problems with the databases is many of them have failure rate numbers, but very few of them have any failure mode distributions. So in reality, what one must do is take a look at both failure rates and failure modes. So we're going to have to gather up this information. As we go about the process of gathering up the failure rate information, what do we have to think about? Well, three primary categories of things impact failure rates of components. Number one, the design of the component. How strong is it? how well will it resist the stresses of the environment? That's one category. Number two, how is the component used in a product level design? What are the stress conditions? Ambient temperature, temperature cycling have a big impact on electronic components. Mechanical cycling, mechanical stress levels have a major impact on mechanical components. So that's the second category, the design of the component, how the component is used, and finally, how the product is used. What is the average, for example, temperature environment of a pressure transmitter? All three of these major categories must be considered in order to have reasonably good failure rate data. Therefore, I will say at Exeter, we couldn't find any material published that was suitable for FMEDA analysis work. And so our researchers at Exeter spent several years creating the Component Reliability Handbook. The Component Reliability Handbook provides failure rates, failure modes, mode distribution, and useful life data for hundreds of components, typically those used in instrumentation equipment. In order to deal with category number 3, the product use, operating profiles were defined. And we're talking about environmental profiles. For each specific profile, there are international standards that define temperature ranges, temperature cycling, humidity, electrical stress, surge, electrostatic discharge. There's a pile of international standards that have defined categories of usage for industrial control equipment. So this part was easy. We just used the profiles that were defined in the IEC standards, and for Exeter we use cabinet-mounted equipment, 2-wire field products, and 4-wire field products. This gives us a complete set of environmental categories. Now, we still have to take into account, one must take into account how a component is used in a product design. And of course, for example, if you were an electronic designer and you chose a resistor, you might very well have that component dissipating very little power or moderate power or high power. Some components are used in external interfaces where they are exposed to higher levels of electrical stress. All these things have a big impact, so you would expect to see different failure rates for these different use categories. And therefore, of course, the component handbook that you should use has these different categories. And these different categories and different profiles effectively form a large matrix. So for any given component type and any given strength design, the matrix of component use and profiles gives you a matrix of different failure rates and failure modes. That combination, while it sounds a little complicated, gives you very reasonable and accurate results. Of course, anyone would be well advised to follow IEC standards whenever possible. And the bulk of the failure rates in the Exeter Component Handbook come from IEC 62380. To verify, we've gathered a lot of independent sources of failure rate data, and we've taken a look at all of these independent sources with a group looking for any particular problems. And IEC is used as the primary source, and it's overridden only if the numbers turn out to be on the low side of other reference sources. Why? For FMEDA analysis, one must be conservative. Occasionally, we found some of the 62380 failure rate numbers do not appear at all to be conservative. And so they're overridden and other sources are used. The useful life is also an important part of the situation because components wear out. Many of you may think about that this is an issue only for mechanical components, and in fact, it's a big issue for mechanical components. I'm thinking O-rings, I'm thinking springs, I'm thinking relay contacts. There are wear-out mechanisms in electronic parts. Those of you who are experienced electronic designers, there's probably a component that pops into your mind. The notorious electrolytic capacitor. Look it up on the internet. You'll find all kinds of stories about wear-out mechanisms of electrolytic capacitors, and even and lots of detail about formulas and how to calculate failure rate as a function of useful life and the useful life. So an FMEDA generates both the constant failure rate during useful life and end-of-life numbers. No component database would be worthwhile if it wasn't constantly being compared to real results. And I will tell you that the research group I work with typically at Exeter constantly compares real field failure data and the product level failure rates to the FMEDA results. I consider this an advantage of the FMEDA technique because it generates product level failure rates by adding up all the failure rates of the modes that you can compare to field failure data, even when you don't have as much field failure data as you like. And what I mean by that is often you need a lot more data points to get failure modes than total failure rate. So in many cases, we're able to gather enough field failure data to calculate a product failure rate. And of course, one must compare that then with the FMEDA results. And what we expect to see is very comparable numbers. And if they're not, then if there is a significant difference, then there must be something wrong with the component database, and one must dig in to see what these differences really are. We do that on a quarterly basis around here, and we are constantly updating the component database to be more accurate and more realistic of industrial process control. Anybody in the audience ever hear the term fault injection testing? It's kind of a fun thing. I view it as really fun for the kind of people who used to destroy things when they were children. Did you like to build blocks, or did you like to go in and smash the building that you made? Fault injection testing is as much fun as smashing those building blocks ever was. And I liked to do that. I like to build and then smash. But in fault injection testing, you go in and come up with means to simulate component failures. Like if resistor R7 fails short circuit, that's easy. We just short circuit with typically a little pair of sharp needle nose tweezers resistor R7. And we check to make sure that the instrument performs exactly as the FMEDA predicted. FMEDA is actually used to generate a set of fault injection tests, and when the fault injection tests are run, we confirm the accuracy of an FMEDA. For 61508 certification, if you claim diagnostic coverage factors above 90%, you're required to verify those numbers with fault injection testing. In other words, if you have a good diagnostic coverage factor, it's not enough to do an FMEDA. The FMEDA must be verified with good fault injection testing. And of course, the FMEDA can be used to document fault injection test results. I will tell you that I think FMEDAs are boring, but fault injection testing is not. Sometimes sparks fly, and it can be a lot of fun. If anyone has any questions, please feel free to type them in. I have a question and answer text box on my screen, and I've been periodically looking but I haven't seen any questions yet. If you have a question, please feel free to type it into the Q&A box, and I can give people a verbal or, if possible, a textual answer, a text answer. If anybody has any questions that come up later after the seminar, do not hesitate to send me an email, and I'll do my best to answer them in a timely manner. For those of you who would like to dig in and learn a little more about FMEDAs, there are several technical papers on the Exida website. There's a technical paper on development of a mechanical failure mode database. There's a technical paper on field failure data, primarily the limitations of field failure data, and a technical paper on FMEDAs, which explains much of this seminar in writing. So if something didn't make sense, don't hesitate to go back to this particular paper and read it. They're all available as free downloads over the Exida website. I do not see any questions, so I'll assume everybody is comfortable enough for now. I would like to thank everyone for participating. Oh, some questions came up. Now I see them. Question: where does FMEDA fall in the safety life cycle of an SIS system? An FMEDA is typically done during product development when a product is certified per 61508. Many manufacturers are having FMEDAs done even if they don't get full product certification. And there is a list of products that have been 61508 certified, as well as a list of products that have been that only have FMEDAs on the Exida website. Go to the home page, and right in the middle of the home page there's an area marked Safety Automation Equipment List. Link into that list and you'll see a list of all products that have had FMEDAs done, as well as products that have had certifications done. Another question: where can we get the FMEDA data for industrial use? FMEDA data are done per the profiles, the environmental profiles that we talked about, and they are most instruments are done for industrial use, and most of those consider worst case industrial use, which most certainly would include oil and gas. The FMEDA data for these instruments is available, for all of these instruments is available in the Exida Safety Equipment Reliability Handbook. It's also available online with the online version of the Exida Safety Equipment Reliability Handbook. And lastly, all of the FMEDA data, as well as generic data, is built in to the Excellentia tool. Quite frankly, that's the tool I use because I try to get stuff done. I don't like to type in data. I love to have that data available for me at the click of a button. Next question: historically, have FMEDAs been initially conservative when updated with field data? Oh, good question. That's from Joe. Thank you. The answer is yes. Traditionally, for the most part, FMEDAs were initially conservative. And over the years, the component database has lower failure rate numbers in it. And the key concept there is you start out, the less you know, the more conservative you must be. And so I will tell you as a fact, the Exida component database has, as more and more data has been included, has lower failure rates in it, or conservative that is more accurate and not necessarily forcibly conservative. Next question: how do you handle fault injection testing of mechanical components, such as valves and actuators? Another good question. Fault injection testing can most certainly be done on mechanical components. Normally that requires a certain amount of destruction that's harder to do than just a pair of tweezers shorting out a resistor. To simulate a small leakage in an O-ring, one would look at the O-ring, pick the point on the O-ring that is most critical, if there are any sections that are most critical, cut the O-ring and reassemble the instrument and see how it works. I've done that with gaskets, I've done it with O-rings, I've done it with diaphragms. For springs, for example, you actually have to damage the spring, tear the instrument apart, damage the spring, reassemble it, and see how it works with the damaged spring. So it takes a bit more work, but it can be done. Next question. For the FMEDA, should we verify every component? Yes, absolutely. And I'm not certain. Well, let me be clear. Every component must be included in the FMEDA. Every component that has an impact on the safety function. The only time you might exclude a component, for example, is if a component could not cause a false trip or could have no impact on the safety function, like an LED, for example, which has no impact on an automatic safety function. Every component must be included. That doesn't mean that every component must be fault injected. For fault injection testing, a sampling of components is done. The sampling is selected to pick components that impact every known diagnostic and every known failure mode. All right, thank you very much for the questions. Let me just make sure I have them all. Okay, looks like I've got them all. If anybody has a question that pops up later, please feel free to send an email. And I hope you have a much better understanding of the FMEDA process. Thank you all for attending. Goodbye.